As I mentioned before, if there are things that are quite interesting but not really central to the topic of Newtonian Sobolev functions, I will make bonus videos on them that hopefully will be shorter and will be benefiting those who are looking for extra material. The first one talks about the notion of BV functions and compares them to absolute continuity. So a function defined in a compact interval in R is called BV if the total variation is finite. That is, if you look at this summation of oscillations of f over all possible finite partitions of AB, and still we get finite value, then the function is a BV. The easiest examples are increasing functions. Even if they are discontinuous, as in this picture, the total variation is finite. And this is because there is no sign switching in these. So therefore, you can remove the absolute value. And once you remove the absolute value, there is telescoping. This is not a union of disjoint intervals. This is a partition. So we see that xj appears here, and then next time it will appear in the first one. So the telescoping will just be the final value minus the initial value of f. The counter-Vitali function is increasing, so it's also of BV. We have the important theorem that BV functions are differentiable almost everywhere. So they have a derivative, but again we see that but the fundamental theorem of calculus can fail for them, as both of these examples here and here show that. We even looked at the simpler even example of constant function and then a different constant value. So it's differentiable almost everywhere, but the FTC fails. And then we saw that the absolutely continuous functions, the class of absolutely continuous functions on compact interval is a subset of BV functions. And for these we have, and this is exactly the class, the largest class where FTC holds, which we have talked in the past 2 videos about. Now the bonus question here I have for you is we can use this total variation what we can use, we can say we can extend this total variation, this definition above. So this supremum value is the total variation of f, say, over the interval AB. But we can do it for other intervals, same way. And then we can extend total variation to a measure on, I have to say, on an outer measure, so that we can define it on all subsets. So an outer measure on AB, so that for every subset of AB, we can associate a number through coverings and then taking infimum over all open sets that cover that. So all you need is to define it for open intervals, and from that you can define it for any set by making it actually in a regular. Anyway, now my question is, which you can ponder about and try to put your answer in the comments, is that is it true that a function f from AB into R is absolutely continuous if and only if this total variation measure is absolutely continuous with respect to a Lebesgue measure, L1. And this absolute continuity of one measure with respect to another measure, maybe you will recall it with this notation. So which means that mu of a set will be 0 if the new measure of that is 0. I think this implies by that absolute continuity of integrals that then mu of e is smaller than epsilon if nu of e is less than delta. So for every epsilon positive, there exists delta positive for this property. But now I'm asking, is there a connection between absolute continuity of measure with respect to another measure and absolute continuity of a function? Let me do some of the obvious examples for you to motivate it. If we look at this function here, the total variation measure will be the delta Dirac function at this point P. So that this measure, if we call this the total variation measure of this function, then this measure of a set will be 1, not 1 actually, it will be like this gap here, this jump. Let's say it is 1. So 1 if P belongs to A, and it will be 0 otherwise, which is exactly capturing the fact that if you have a segment and you calculate the total variation, it will be 0 if the segment lies only here or here. And if you have a segment, no matter how small it is, if you jump from two sides, then you calculate total variation. If you take a partition with just 2 points on opposite sides, then you get at least 1. And actually not more than 1. And in this case, we see that this function is not absolutely continuous, but also we see that, so f is not, in this case, absolutely continuous. But then we also see that this measure is not absolutely continuous with respect to L1 measure, because, well, L1 of a point of this set is 0, but mu of that 1 point is 1, which is not equal to 0. So, back to the question, is it true that these two conditions are indeed equivalent, which will make the terminology then quite well done? And let's say that's the end of my bonus video 1.